Something extraordinary is happening right now in our solar system. And I need to tell you, the physics behind what we're witnessing is unclear, deeply unclear, in a way that's forcing some of the brightest minds in astrophysics to question assumptions we've held for decades. According to a new image released by Tiasak Taluang from a 0.26-meter telescope in Thailand, the interstellar comet 3I Atlas is displaying an anti-tail. Not just any anti-tail, but one that extends nearly 1 million kilometers through space, pointing directly toward the Sun, that's roughly 3 times the distance from the Earth to the Moon. Now, for those unfamiliar with cometary physics, this shouldn't be possible. A comet's tail always points away from the Sun, pushed outward by solar radiation pressure and the solar wind. That's basic physics. That's what we teach in undergraduate courses. But 3I Atlas is doing the opposite. And here's what makes this truly remarkable. The anti-tail isn't just pointing toward the Sun, it's penetrating through the solar wind at speeds that suggest something far more energetic than typical cometary outgassing. We're talking about a tightly collimated jet that's punching through plasma, moving at 400 kilometers per second. For a natural comet, this could be associated with the release of giant dust particles with an effective radius of 10 to 100 micrometers. These particles are 1 million times more massive than the typical micrometer scale dust which scatters sunlight most effectively. But here's the problem with that explanation. The amount of mass loss required would be extraordinary, 100 times larger than normal cometary activity to produce the same brightness. There's another possibility. Instead of refractory dust particles that survive solar heating, the scattering of sunlight could be produced by fragments of ice that get evaporated before having a chance to turn around and produce a traditional cometary tail away from the Sun. And then there's the more speculative possibility, the one that makes traditional comet scientists uncomfortable, that the anti-tail is a result of technological thrusters which accelerate 3I Atlas away from the Sun through tightly collimated jets that penetrate 1 million kilometers through the solar wind because of their high speed. Future spectroscopic data will be able to calibrate the outflow speed and distinguish between natural outgassing, which results in a characteristic speed of up to a few hundred meters per second, and artificial jets, which produce speeds above a few kilometers per second. Figuring things out through the collection of data resembles the work of a detective, and with the flood of data on 3I Atlas, in the coming weeks leading to its closest approach to Earth on the 19th of December 2025, we should be able to figure out its nature. But right now, what we're seeing is deeply puzzling, and it's about to get even stranger. The latest images from the 5th of November 2025, taken by both the Lowell Discovery Telescope in Arizona and the Arnaves Observatory in Spain, show something peculiar, something that doesn't fit any model we have for how comets should behave. Despite passing through perihelion on the 29th of October 2025, at a distance of 1.36 astronomical units from the Sun, the expected massive cometary tail pointing away from the Sun is conspicuously absent. Let me repeat that. This comet just passed through its closest approach to the Sun. This is when comets are supposed to be at their most active. This is when we should see spectacular tails streaming millions of kilometers into space. But instead, we see a compact source of light, a fuzzy ball surrounded by a coma that is not very different in morphology from its appearance in the Hubble Space Telescope back on the 21st of July 2025. This is deeply puzzling. For context, when I calculated the mass loss from 3I Atlas based on NASA's Jet Propulsion Laboratory report of non-gravitational acceleration, the result was startling. The momentum conservation equation suggested that more than 13% of the comet's initial mass should have been ejected during its perihelion passage. Think about that for a moment. 13% of its entire mass. For any typical comet, such massive mass loss would create a spectacular tail, a vast plume of dust and gas pushed by solar radiation pressure and the solar wind into the classic cometary shape we all recognize. Yet the November images show no such tail. Compare this to Comet Leonard from our own solar system. Photographed by the same Naves Observatory just 2 days earlier on the 3rd of November 2025, Leonard displays exactly what we expect: a clear, prominent cometary tail streaming away from the sun. The contrast is striking and demands explanation. The mystery deepens when we consider the Europa Clipper spacecraft, which was positioned between October 30th and the 6th of November 2025 to potentially pass through the ion tail of 3I Atlas. Samuel Grant from the Finnish Meteorological Institute and Geraint Jones from the European Space Agency predicted this rare alignment using their tail catcher computer model. The opportunity was extraordinary, a chance to directly sample material from an object that originated beyond our solar system. The spacecraft carries plasma instruments and magnetometers specifically designed to detect ions and magnetic field changes. If 3I Atlas is a natural comet with the kind of mass loss we calculated, Europa Clipper should have encountered a substantial stream of charged particles carried by the solar wind. The results from this encounter, when they become available, will be crucial. The absence of a visible tail in post-perihelion images raises a fundamental question. Where did all that mass go? If the comet is natural and lost over 13% of its mass, that material must be somewhere. The lack of a visible dust tail suggests either that the ejected material is different from what we expect, or that the outgassing mechanism is fundamentally different from normal cometary activity. This brings me back to the technological hypothesis that some have criticized me for entertaining. Chemical rockets, which humanity uses for space propulsion, operate with exhaust velocities of 3 to 5 kilometers per second. That's roughly 10 times faster than the maximum ejection speed of volatiles sublimated by sunlight from cometary surfaces. A technological propulsion system would deliver the required momentum with far less ejected mass and at much higher velocities. The jets would be more collimated, more directed, potentially explaining both the anti-tail phenomenon and the absence of a dispersed dust tail. Now, I'm not claiming 3I Atlas is a spacecraft, but I am saying that the observations we're gathering don't quite fit the standard natural comet model. And when observations don't match predictions in physics, we have a responsibility to explore alternative hypotheses, no matter how unconventional they might seem. The spectroscopic data we have gathered so far add more layers to this puzzle, and what they reveal is extraordinary. Observations from the James Webb Space Telescope in August 2025 revealed that 3I Atlas has an extraordinarily high carbon dioxide to water ratio, approximately 7.6 to 1, or roughly 8 to 1. This is among the highest ever observed in any comet, sitting 4.5 sigma above the trend seen in solar system comets. Let me put that in perspective. In statistics, when something is 4.5 sigma above the trend, it means it's so unusual that it would occur by random chance less than once in every 300,000 observations. This isn't just slightly odd, this is profoundly anomalous. The comet was emitting about 129 kilograms of carbon dioxide per second, but only 6.6 kilograms of water per second, along with 14 kilograms of carbon monoxide per second and small amounts of carbonyl sulfide. This extreme CO2 enrichment tells us something profound about 3I Atlas. One possibility is that it formed in a region of its parent stellar system that was unusually rich in carbon dioxide, perhaps near a CO2 ice line. Different star systems have different chemical compositions, and the snow lines where various volatiles freeze out occur at different distances, depending on the star's luminosity and the protoplanetary disk's properties. But there's another intriguing possibility suggested by recent research. The outer layers of 3I Atlas may have been processed by galactic cosmic rays during billions of years of travel through interstellar space. Laboratory experiments demonstrate that cosmic ray irradiation efficiently converts carbon monoxide to carbon dioxide while synthesizing organic rich crusts. The depth of this processed layer could extend 15 to 20 meters into the nucleus. If this cosmic ray processing hypothesis is correct, it represents a paradigm shift in how we think about interstellar objects. Rather than pristine samples from other planetary systems, they may primarily reveal material that has been transformed by eons of exposure to the harsh radiation environment of interstellar space. The erosion rate of 3I Atlas suggests that current outgassing only samples this processed zone, never reaching the pristine interior material that might tell us about the comet's original formation environment. Think about that. We might be looking at an object whose surface has been fundamentally altered by billions of years of cosmic ray bombardment. The chemistry we're measuring might not represent where it came from, but rather what happened to it during its long journey through the void. The Very Large Telescope detected cyanide gas and atomic nickel vapor in the coma of 3I Atlas at concentrations similar to those in solar system comets. Interestingly, early measurements showed an unusually high nickel to iron ratio, with strong nickel emission but weak iron. A puzzling imbalance that began to normalize as the comet approached the Sun. This evolving ratio may reflect temperature-dependent release of metals or differences in the chemical pathways that formed the original ices. It provides a rare glimpse into the metal content of interstellar matter. The Swift Observatory's tentative detection of water vapor and hydroxyl ions came as a surprise because it occurred when 3I Atlas was at a distance from the Sun, usually insufficient for such activity. This early activity suggested the presence of highly volatile compounds like carbon dioxide and carbon monoxide that sublimate at much lower temperatures than water ice. The rapid sublimation of CO2 may create evaporative cooling, absorbing heat from the surface and lowering local temperature, thereby delaying the onset of water sublimation. This could explain why we see so much carbon dioxide relative to water. The optical and near-infrared spectroscopy revealed a red spectral slope, approximately 18 to 22% per 1,000 angstroms in the visible range. This redness is greater than most solar system comets, but similar to some trans-Neptunian objects and centaurs, as well as D-type asteroids. The reddening could indicate extensive space weathering, the chemical alteration of surface material by exposure to interstellar radiation and cosmic rays over billions of years. Spectral modeling suggests a composition of roughly 70% Tagish Lake meteorite-like material and 30% 1 micrometer-sized water ice grains. Now, here's where things get really interesting from a statistical standpoint. What makes 3I Atlas particularly anomalous is its sheer size relative to other known interstellar objects. Its inferred mass is over 1 million times greater than that of Oumuamua. Let that sink in for a moment. 1 million times greater. The nucleus diameter, while uncertain because we cannot separate its light from the coma, is estimated to be between 0.32 and 5.6 kilometers, with most likely values under 1 kilometer. But even at the lower end of estimates, this raises a statistical puzzle I outlined in my first paper on 3I Atlas. Why have we found such a giant object before witnessing 1 million objects of the size of Oumuamua? There is not enough rocky material in interstellar space to accommodate the delivery of such a giant icy rock to the inner solar system over our survey period of about a decade. Based on our understanding of the population of interstellar objects, we would expect an object with a diameter above 10 kilometers to be delivered to our vicinity once per 10,000 years or longer. The fact that we discovered 3I Atlas so soon after beginning to seriously look for interstellar objects suggests either that we have been extraordinarily lucky or that our assumptions about the population of interstellar objects need revision, and luck is not a scientific explanation. The trajectory of 3I Atlas is itself remarkable. Its orbital eccentricity of 6.139 is extremely high. The highest of the three confirmed interstellar objects, greater than Oumuamua's eccentricity of 1.2 and Borisov's eccentricity of 3.4. This extreme eccentricity makes the trajectory appear relatively straight rather than curved. At perihelion, the comet was moving at its maximum speed of 68 kilometers per second with respect to the Sun, projected to infinity. Its heliocentric radial velocity is approximately 58 kilometers per second. Dynamical modeling suggests that this high velocity is consistent with a relatively large dynamical age of 3 to 11 billion years. If 3I Atlas originated from the thick disk of the Milky Way rather than the thin disk where most stars reside, the comet could be at least 7 billion years old, older than our solar system itself, which formed 4.6 billion years ago. This would make it the oldest comet ever recorded. Such an ancient visitor would have witnessed the formation of our solar system from afar, carrying with it information about stellar environments that existed when the universe was half its current age. The complex jet structures observed in early November images are also noteworthy. On the 11th of November 2025, the Virtual Telescope project captured images showing intricate jet patterns, 4 to 5 tails or jets fanning out in multiple directions. Some commenters noted that these structures resemble those seen in Comet C/2016 R2, an unusual long-period comet extremely rich in carbon monoxide and nitrogen, but poor in dust. The morphology suggests that 3I Atlas may have been significantly altered by its close pass near the Sun. Now, let me address something that's been frustrating for the scientific community, as often happens with comets. During the government shutdown that lasted 42 days in the United States, there were bureaucratic obstacles to sharing observational data. The high-rise camera on the Mars Reconnaissance Orbiter was positioned to image 3I Atlas when it passed within 29 million kilometers of Mars on the 3rd of October 2025, but the images have not yet been released. The HiRISE website releases new Mars images daily, but singled out 3I Atlas with a notice stating that any images of the interstellar comet are considered NASA news. And because of the government shutdown, communications of NASA news have been suspended. This is unfortunate. Science should not be held hostage by bureaucracy. Fortunately, other Mars assets did observe the comet. The European Space Agency's Trace Gas Orbiter and Mars Express both captured observations between October 1st and 7th, 2025. The Trace Gas Orbiter successfully imaged the comet, though Mars Express did not detect it, likely due to a much lower exposure time. China's Tianwen-1 orbiter also managed to image 3I Atlas during this period. These observations from multiple spacecraft provided valuable data about the comet's activity near Mars orbit, the Hera spacecraft. On its way to the Didymos-Dimorphos binary asteroid system impacted by the DART mission, also had a potential opportunity to sample the ion tail of 3I Atlas between October 25th and the 1st of November 2025. However, HERA lacks the appropriate instruments to detect the ions or magnetic draping structure associated with the comet's interaction with the solar wind. Nevertheless, the alignment offered the chance to measure any changes in the local space environment as the spacecraft passed through the extended tail region. Looking ahead, several spacecraft are positioned to provide additional observations as 3I Atlas continues its journey out of the solar system. The Juno spacecraft orbiting Jupiter may be able to observe the comet when it passes close to Jupiter in March 2026, though redirection is unlikely because Juno is low on fuel and has issues with its engine. The Psyche spacecraft passed about 45 million kilometers from 3I Atlas on the 4th of September 2025, while the Jupiter Icy Moons Explorer passed within 64 million kilometers around the same time. The Webb telescope is scheduled to make its next observations of 3I Atlas in December 2025 after perihelion. These observations will be absolutely critical. The spectroscopic data will determine the velocity, mass flux, and composition of the jets with unprecedented precision. If the outflow velocities are in the few hundred meters per second range typical of natural outgassing, we will have confirmation of the comet's natural origin. If velocities exceed a few kilometers per second, we will need to seriously consider artificial propulsion. The Hubble Space Telescope has also conducted ultraviolet spectroscopy in November 2025 to determine the composition of gas emissions and measure the sulfur to oxygen ratio. Hubble will continue monitoring 3I Atlas as it moves away from the Sun, providing long-term data on how the comet's activity evolves with changing solar distance. The combination of ultraviolet, optical, and infrared observations across multiple epochs will paint a comprehensive picture of this mysterious visitor. As 3I Atlas approaches its closest point to Earth on the 19th of December 2025, at a safe distance of 1.8 astronomical units, ground-based telescopes will have their best opportunity for detailed observations. The comet is expected to shine at magnitude 11 to 12, too faint for the naked eye, visible only through good binoculars under ideal dark sky conditions, but readily observable with small telescopes. It will move through the constellations, Virgo and Leo, climbing higher in the morning sky with each passing day. Now, let me draw some parallels between 3I Atlas and the earlier interstellar visitor Oumuamua because the similarities are worth considering. Both objects displayed unusual characteristics that challenged our assumptions. Oumuamua's extreme elongation, its peculiar acceleration away from the Sun without visible outgassing, and its tumbling motion all sparked scientific debate. I suggested in my published work that Oumuamua could be a light sail, a thin artificial object designed for interstellar travel using radiation pressure. The scientific community was divided, with many insisting it must be a natural object despite the anomalies. Now with 3I Atlas, we face similar questions but with more data. Unlike Oumuamua, which we discovered on its way out of the solar system when it was already too late for comprehensive observations, 3I Atlas was detected on its way in. We have had months to study it with humanity's most powerful telescopes. We have spectroscopic data revealing its composition. We have images showing its morphology. We have a spacecraft positioned to sample its tail. And yet the anomalies remain. The missing dust tail, the extreme CO2 enrichment, the size anomaly, the anti-tail structure. The conservative interpretation attributes all these features to natural processes, cosmic ray processing, unusual formation conditions, and fortuitous statistics. And this may well be correct. Nature is endlessly creative, producing phenomena that often surprise us. The burden of proof for an extraordinary claim like artificial origin rightly rests on proponents of that hypothesis. But science advances by considering all possibilities consistent with the data, then using observation and experiment to eliminate those that cannot be true. The appropriate scientific stance is neither reflexive skepticism nor uncritical acceptance, but rather careful analysis of what the evidence actually shows. My role, as I see it, is to ensure that we ask all the relevant questions and do not prematurely close off lines of inquiry simply because they make us uncomfortable. I'm reminded of a conversation I had with a colleague who studies machine learning. They pointed out that AI systems are typically trained on data sets representing known classes of objects. When you train an AI to recognize asteroids and comets using only solar system examples, it will naturally try to classify everything it encounters into those categories. Even if the object belongs to a fundamentally different class, this is not a flaw in the AI. It is working exactly as designed, but it highlights the importance of human scientists remaining open to possibilities beyond our training data. We should add to our conceptual framework all the technological objects that humanity has launched into space. We should remember that on the 2nd of January 2025, the Minor Planet Center initially catalogued a near-Earth asteroid that turned out to be Elon Musk's Tesla Roadster. If we can confuse our own technology for natural objects, how confident should we be in our classifications of visitors from other stellar systems? The discovery of interstellar comet C/2025 V1 by Gennady Borisov, who also discovered 2I/Borisov in 2019, on the 2nd of November 2025, adds another dimension to our discussion. This new object has an orbital eccentricity of 1.0095, with an uncertainty of 0.0026, putting it tantalizingly close to being interstellar, but most likely originating from the Oort cloud at the outskirts of our solar system. A small gravitational impulse from Jupiter near perihelion is sufficient to make a bound Oort cloud object appear slightly hyperbolic. Interestingly, C/2025 V1, like 3I Atlas, does not display a clear cometary tail. This similarity may tell us something about a class of objects we have not adequately characterized. The rate at which we are discovering these unusual visitors suggests we are only beginning to uncover a much larger population of objects moving through our cosmic neighborhood. With the Vera C. Rubin Observatory set to begin operations soon, our survey capabilities will increase dramatically. The Rubin Observatory will discover thousands of new objects each night, allowing us to build a comprehensive census of what travels through interstellar space. Only then will we understand how typical or anomalous objects like 3I Atlas truly are. What strikes me most about the public response to 3I Atlas is the genuine curiosity and wonder it has inspired. My inbox has been flooded with messages from people around the world. Parents write that their children eagerly await updates on the comet. Teachers tell me they are using 3I Atlas to spark interest in science and astronomy. A young person questioning their engineering career path wrote that learning about this interstellar visitor reignited their passion for science and reassured them about their future. This is what science should be about: maintaining the privilege of childhood curiosity, the willingness to ask "what if?" without pretending to know the answers in advance. The opportunity to learn something genuinely new from a blind date with a mysterious interstellar object excites not just professional astronomers, but the broader public. Despite what some influencers claim, the foundation of science is the humility to learn. not the arrogance of expertise. I hope that the data we collect in December, especially around the closest approach to Earth on December 19th, will reveal the true nature of this interstellar object. The Webb telescope observations will measure outflow velocities with enough precision to distinguish between natural and artificial propulsion. The ground-based spectroscopy will track how the composition evolves as the comet recedes from the Sun. The imaging campaigns will document whether the coma morphology changes in ways consistent with natural outgassing or suggests something else. Whatever we discover, 3. Atlas has already succeeded in one crucial mission, reminding us that the universe is full of surprises, that our models and assumptions are provisional, and that the greatest discoveries often come from objects and phenomena that do not fit neatly into our existing categories. Whether this visitor from the stars is a comet shaped by billions of years of cosmic ray processing or something more exotic, it has expanded our understanding of what is possible. As this interstellar traveler continues on its hyperbolic trajectory past Earth in December, past Jupiter in March 2026, and then back into the vast darkness between the stars, we have a limited window to extract every bit of information we can. This may be our only chance to study such an object up close for decades or centuries. We must make the most of it. The saga of 3I Atlas is far from over. In the coming weeks, as telescopes around the world and in space turn their attention to this cosmic visitor, we will gather the evidence needed to solve its mysteries. The anti-tale persists, the tales evolve, the composition challenges our assumptions, and somewhere in all this data lies the truth about where this object came from, how it formed, and what its journey through the galaxy has made of it. Let us hope that 3I Atlas does not deliver any unwanted gifts during the holiday season, but instead offers us the greatest gift science can provide: new knowledge about the universe and our place within it. The answers are out there, encoded in photons that have bounced off this ancient traveler. Our task now is to read those messages correctly, with open minds and rigorous methods, letting the evidence guide us to conclusions rather than forcing the evidence to fit our preconceptions. In the end, that is what science demands of us: intellectual honesty, methodical analysis, and the courage to follow the data wherever it leads. Now let me address what I think is the most important question facing us right now. Not what 3I Atlas is, but what it means for how we do science in the 21st century. We live in an era where our instruments are powerful enough to detect objects from other star systems. We can analyze their composition, track their trajectories, and search for anomalies that might indicate something beyond natural processes. But our institutional frameworks, our peer review systems, our funding mechanisms, they're all built around the assumption that everything we observe will fit into existing categories: natural or artificial, comet or asteroid, known or unknown. 3I Atlas is teaching us that reality doesn't always cooperate with our categories. It's showing us that there's a vast middle ground between definitely natural and definitely artificial, where objects can display characteristics that challenge both classifications. And in that middle ground, we need new approaches, new ways of thinking, new frameworks for analysis. The traditional scientific method works beautifully when you're studying phenomena that fit established patterns. You form a hypothesis, design an experiment, collect data, and either confirm or reject your hypothesis. But what do you do when the phenomenon itself is so unusual that you don't even know what hypotheses to test? When every explanation you can think of seems to require special pleading or unlikely coincidences? That's where we are with 3I Atlas. We have multiple competing hypotheses, each with its own strengths and weaknesses. and the data we're collecting isn't cleanly supporting any single explanation. The natural comet hypothesis requires us to invoke cosmic ray processing, unusual formation conditions, and statistical flukes. The technological hypothesis requires us to accept that we might be observing evidence of extraterrestrial engineering. Neither is comfortable, neither is simple, and that's okay, because the universe doesn't owe us comfortable, simple answers. It is what it is, regardless of our preferences or preconceptions. What we need is a framework that allows us to hold multiple hypotheses simultaneously, weighing them against incoming data without prematurely committing to any single explanation. We need what I call epistemic humility, the recognition that our current understanding might be incomplete or even fundamentally wrong in ways we can't yet perceive. This doesn't mean abandoning rigor or accepting wild speculation. It means being honest about the limits of our knowledge and being willing to revise our understanding when the evidence demands it. 3i Atlas is providing us with that evidence. The question is whether we're willing to listen. The anti-tail phenomenon alone should give us pause. Yes, we can construct natural explanations involving giant dust particles or ice fragments, but those explanations require very specific conditions that we've never observed before in any comet. The missing dust tail after perihelion is another puzzle. Where did 13% of the comet's mass go if not into a visible tail? We can speculate about high-velocity jets or unusual particle sizes, but we're essentially inventing new physics to explain the observations. The extreme CO2 enrichment, the size anomaly, the trajectory characteristics. Each of these individually might be explainable, but together they form a pattern that's statistically improbable. And when you're dealing with statistically improbable patterns, you have two choices. You can assume you've witnessed a rare but natural occurrence, or you can consider that your assumptions about what's natural might need revision. I'm not advocating for either position. I'm advocating for honest, open-minded analysis that follows the data wherever it leads. The spectroscopic observations scheduled for December will be crucial. If we measure outflow velocities in the few hundred meters per second range, that strongly supports natural outgassing. If we measure velocities of several kilometers per second, that's much harder to explain naturally. The trajectory analysis will also be telling if 3i Atlas continues to show non-gravitational accelerations that can't be explained by observed outgassing. That's a significant anomaly. And the long-term monitoring as it moves away from the Sun will show us whether the activity patterns are consistent with natural sublimation or suggest something else. We're living through a moment of genuine scientific uncertainty, a moment where the data is ambiguous enough that reasonable scientists can disagree about interpretation. That's uncomfortable. We like certainty, we like clear answers, but sometimes the most honest answer is, we don't know yet. And that's where we are with 3i Atlas. We don't know yet. But we're gathering the data that will eventually tell us. In the meantime, we need to resist the temptation to force premature conclusions. We need to let the evidence accumulate. We need to remain open to possibilities that might challenge our worldview. Because if there's one thing I've learned in decades of studying the cosmos, it's that the universe is always stranger and more wonderful than we imagine. 3i Atlas might be a natural comet with unusual but explicable characteristics, or it might be something that forces us to expand our understanding of what's possible in the universe. Either way, we're witnessing something extraordinary, and we have a responsibility to approach it with the rigor, honesty, and open-mindedness that science demands. The continuing saga of anti-tails and tails around 3i Atlas is more than just an astronomical curiosity. It's a test of how we do science in an age where our instruments can detect phenomena that challenge our existing frameworks. Are we up to that challenge? Can we set aside our preconceptions and follow the evidence wherever it leads? I believe we can. I believe we must. Because the alternative, clinging to comfortable assumptions in the face of contradictory evidence, is not science, it's dogma. And dogma has no place in the pursuit of truth. So as we watch 3i Atlas make its closest approach to Earth this December, let's commit to following the data, let's commit to honest analysis, let's commit to asking the hard questions, even when the answers might be uncomfortable, because that's what science is, not a collection of facts, but a method for discovering truth. A method that requires courage, humility, and an unwavering commitment to following the evidence wherever it leads. 3i Atlas is giving us that evidence. Now it's up to us to have the courage to see what it's telling us. Thank you for joining me on this journey through one of the most intriguing astronomical discoveries of our time. The story is still unfolding. The most important observations are yet to come. Keep watching the skies. Keep asking questions. Keep demanding that we follow the evidence, not our assumptions, because somewhere in the data, streaming back from telescopes around the world, somewhere in the spectroscopic signatures and trajectory calculations, somewhere in the patterns we're only beginning to recognize, lies the truth about 3i Atlas. And whatever that truth turns out to be, it will teach us something profound about the universe and our place within it. The continuing saga of 3i Atlas is our saga too, a reminder that we live in a cosmos full of mysteries, waiting to be solved by those brave enough to look beyond the comfortable boundaries of what we think we know. Keep looking up, keep wondering, and remember, the universe is speaking to us through objects like 3i Atlas. We just need to have the